especially in the context, in my case, of galactic star formation. So just to give you a brief introduction, I guess that many of you know what this is. This is our home, the Milky Way, seen by Gaia. And one notable feature is all these dark patches that are obscuring the galactic disk. And these are regions where the gas and the dust content becomes so dense and so cold that it basically block completely the background radiation coming from the background stars, and so they appear as as black patches. The point is that these are giant molecular clouds, which is where all the action in terms of star formation happens, because this is where stars are currently forming and will form in the future. So if we want to really study how the star formation process works, we have to really have a look at this object. Of course, you cannot really do it in optical wavelength because you don't see much. But we can exploit the fact that the electromagnetic spectrum is huge. And so, for instance, we can tune at about 115 gigahertz. And this is the first rotational transition of carbon monoxide, CO, which is not the most abundant molecule in the universe, that being in the interstellar medium, that being H2, of course, but by far the most detectable. And as you can see, those dark patches are really now flaring up in CO emission. And CO is extremely good into tracing the interstellar medium, but it's by far not exhaustive in what it can trace. And in fact, in the last decades, or like half a century, almost 300 molecules have been detected. This list is by far not complete, even because the amount of new detection per month is dramatically increasing, due mainly to the fact that microwave and radio facilities at the moment are really increasing their capabilities in terms of sensitivity and resolution. So, and you can see we go from fairly simple things like, I don't know, CO, ammonia, but now we're really starting to explore molecules with 8, 9, 10 atoms, really digging into this prebiotic world. So the idea of osteochemistry is to use all of this to say something about the star formation process, which ultimately is the life cycle of the interstellar medium. You start with diffuse clouds, which are fairly warm for my standards, around a bit less than 100 Kelvin, and fairly diffuse. And this can condensate into denser object clouds, where the perfect condition for molecules to form and to survive are met. And these clouds tend to fragment into smaller and even denser, even colder pieces, known as prestellar cores, which, at least concerning low-mass stars, is really where the action happens. So these will, when and if growing up stable against gravitational collapse, they will collapse and they will form a central object known as a protostar. Okay. And the protostar is a very active object. In particular, it keeps accreting material from the very dense envelope, which still surrounds it. And it does so usually in form of accretion disk, which is also known as a protoplanetary disk. There is where protoplanets and planets will eventually form. As time goes by, all this activity would basically clear out from all the dust and the gas, the surrounding envelope, and you're left with just a formed stellar system. And this is a cycle, indeed, because it is closed by the fact that stars, especially towards the end of their lifetime, tend to return large amounts of the material that they locked in their interiors back into the gas phase, either through winds or through dramatic explosion, like supernovae, right? So the idea is to follow this cycle, in particular these two phases, of course, I will focus on using molecules. And astrochemistry is an interdisciplinary field which is built on three big pillars. One is lab studies, and this is not an archival image. This is a picture I took in one of the labs that we have at MP in Garching. And when I mean lab, I mean either studying of and characterizing the spectrum of these molecules, telling us the frequency where we should look for these molecules, or characterizing their reaction rates, or even the collisional coefficient, which are crucial to perform radiative transfer studies. Then you have theoretical work, under which is an umbrella under which I put both chemical modeling and hydrodynamical or magnetodynamical modeling, or possibly a combination of both, in order to follow the physics, dynamics, and chemistry evolution of star-forming regions. And finally, you have observations where you go there using mainly radio telescope or radio interferometers to detect this molecule and to characterize their properties. These fields are, of course, deeply interconnected, and they benefit enormously one from another. For most of my work, I am an observer, as you can tell, because this is me in front of my very favorite instrument, which is the 30-meter antenna placed in Sierra Nevada, in Granada. But I also been working extensively, especially in the last year, in the chemical modeling world. So just a last slide. This should be quite obvious, but just so we are all on the same page. What I mean by observing molecule, we will talk about very cold phases of the ISM. So the temperature budget, so the energy budget available is not enough to excite nothing more than basically rotational or at most low vibrational transitions. So we will talk about lines which happens more or less between a few gigahertz up to 1 terahertz. And each line is characterized by two key parameters. One is the critical density, which you can think of as the density of the medium at which this transition is mostly excited, and then the excitation temperature, which regulates the population of the energy levels, which is a proxy more or less for the cast temperature. So basically you can see that by using different species and different transition of the same species, we can basically achieve a tomographic view of star-forming region because we can probe different depth into the source at different regimes of temperature and densities. And we can do marvelous things with this. So I will start to show you a few examples of what can be done. And the first project I would like to talk about deals with kinematics, because of course, because of Doppler shift and because of the line broadening, molecular spectroscopy carries a lot of information on the kinematic properties of the source we are targeting. And this source in particular belongs to this big giant. This is the Taurus molecular cloud, which is one of the best studied low-mass star-forming region, mainly due to its proximity to the solar system. This is a map done with Herschel. So what we're seeing here is the thermal emission of the dust grains embedded in the medium, which are emitting at far infrared wavelengths. And what I would like you to focus on is this tiny tip here, which is one of the best known pre-stellar cores that we have out there. It's called L1544. And in the last few decades, we have really targeted it with a number of observational and theoretical studies, and we know a lot about its structure. L1544 is a low-mass core. It contains about 8 solar masses in total. It will form likely a pretty small star, something smaller than the Sun. And it's exceptional because it's extremely centrally peaked in its density profile, and at the center reaches more or less 6 Kelvin. So we are really seeing the verge of, we're really on the verge of the gravitational collapse. And indeed, we know from previous studies that decontraction has already happened. And how we know it? Well, these are a number of molecules that have been detected toward the center of this core, okay? So you have to imagine that if all these would arise from very static gas doing nothing, they would be perfect Gaussians, more or less, okay? They are clearly not. And this spectral profile, in particular in black, you see in both panels H2O plus 1 to 0, and in blue you see water here. This is an inverse P-Cygni profile, and this is a double peak profile seen also in ammonia. These are typical of when, along the line of sight, you have a contraction motion. So you have two parts of the gas contracting toward the center. This is a signature of inflow. So we know already from a few years that L1544 is also evolved that it's already started contraction. But how extended are these contraction motion? Do they regard only the core or also the envelope, the big envelope surrounding it? This was not well known. And so we went went to the 30-meter telescope in Granada, and we observed a large map of HCO plus 1 to 0, because this is one of the most ideal transitions that we have to perform these kinematic studies. So here what you see in white contours is the H2 column density, so more or less the mass distribution in the source. And the color scale is then the integrated intensity, so the flux of this line. And at all this position, we extract the spectra. And you can see them here, where I'm showing a comparison between something very, very abundant and optically thick, HCO+, and something instead much more optically thin, C18O. C18O is the isotopologue of CO, and by 18O being almost 500, more than 500 times less abundant than the main 16O, it is much, much less abundant as a molecule. And let's zoom in so you can understand what is happening. So what is happening is that the optically thin line, the red line, is more or less Gaussian, right? It's something very close to Gaussian. And it's peaked at the velocity of the source, while the HCO plus spectrum is almost everywhere double peak, with a blue peak, which is this one, much, much brighter than a red peak. And this is because everywhere in the source, HCO plus is tracing this contraction, okay? So we started trying to model it, starting from the center of the source, which is this blue asterisk. And to do that, we exploited the fact that we have a physical model of this source. Here you see in red the gas temperature, the dust temperature in green, then you have density profile in black, and the velocity profile in absolute values in blue. So we have a full one-dimensional model that we can then couple to chemical code that predicts the abundance of our molecules, in particular, in this case, HC+. And then you can put this into very time-expensive code that perform non-LTE radioactive transfer. So it basically propagates photons back and forth until the population of the energy levels of this molecule reaches equilibrium, okay? And then you obtain a model spectrum, this is this red one, which is overimposed to the observed one. This seems fairly decent fit, but it's not. It's not for two main things. The first thing is that the asymmetry between the blue peak and the red peak is not matched at all. And even more importantly, you see that the dip of absorption goes to 0 in the observed spectrum. This is not reproduced by the model, and this is because the model has not enough absorption, okay, to really push down this flux level to 0. So what we did is that we added to this model, which is limited to 0.3 parsec, an envelope, because HCO plus is very abundant also at low densities, so it makes perfect sense that this is a core embedded in a cloud, and the cloud is still full of HCO plus, which is doing something. So we basically, in first order, with 0 order, we simply expanded the model up to 1 parsec, assuming so a uniform and at the beginning static envelope. And we started to see something. The first thing that we saw is that only if we lower this envelope density down to basically less than 50 particles per cubic centimeter, you really reach finally the 0 level dip that you are seeing. This is good, but then the two peaks are almost symmetric now. This is because the envelope is static in this model. So we started to increase an inward velocity, and we saw that when you reach about 0.05 kilometers per second along the line of sight, you finally can see something which is still not ideal, but it's very close to the observations. So only if we imagine that there is a diffuse and very diffuse for my standards and contracting envelope surrounding the core, we are able to reproduce our data. Sorry, this switched without me knowing it. So not only that, of course, we have a map. So we can start to study not only at the center of the core, but in the whole core, this contraction motion. And this is an example of spectra that I extracted and that I fitted with a simple, very simple toy model of contraction. And you can see the fit was decent, and we have everywhere an infill velocity. So the main result of this work was that indeed the HCO plus data are telling us that around this core there is a large envelope which is very diffuse, but it's already contracting. So we cannot really think about just the core contracting alone, but if we want to understand the evolution of these things, we have to study the core cloud connection, okay? And by just incidentally, this is also in agreement with something that was observed recently toward this source, which is the magnetic field through Zeeman effect. And what they notice is that already in the envelope at low densities, the envelope is supercritical. So it must have started gravitational contraction. And indeed, this is what we observed. So kinematics, amazing. What about sources which are not so isolated and placed in a very tip of a giant molecular cloud, having nothing to do with the surrounding environment? Well, molecules can do marvelous things also in this context. And in this project, we were looking into a different regime. We were looking to high mass star forming regions. High mass stars, of course, way rarer than low mass stars, but they really dominate the dynamic and energetic of an interstellar medium, right? And the problem is that they are on average more distant than us. They are very short-lived objects. So many things are still unknown about their formation. And in particular, two kind of families, let's say, of models about how high mass stars form has been developed. One is the turbulent core accretion, which is basically a scaled up of the low mass star formation. You have a big, big core, virialized, that collapses as a whole. And then you have instead clump-fed scenarios or competitive accretion, where you form small cores that keep accreting well through the protostellar stage. What these models predict is very different properties in terms of masses and virialization of the seeds of high mass stars. So how massive are prestellar cores that will form high mass stars? Are they really massive, hundreds of solar masses? Answering this question observationally will provide amazing constraints to the theory, right? The problem is that it's not so easy because high mass stars form in an extremely crowded environment, heavily obscured. So first of all, you need interferometers, otherwise you're not disentangling anything. And second of all, what is a good tracer of prestellar gas? Because we want to find cores, we want to measure their mass, but we want also to be sure that they are not yet in a protostellar phase, right? And we can do this using chemistry. And in particular, using this tiny, tiny molecule, H2D+, which is the deuterated form of H3+. This molecule is peculiar in its chemistry, and the important things that you have to know is that it's very abundant only when the temperature are low, lower than 20 Kelvin, and the density are pretty high, higher than 10 to the 5. So it's really the ideal target to look for prestellar sources. And this is what we did. At the beginning, we targeted these two clumps, where this is apex, so this is their dust thermal emission seen with a single dish. And the result of this work was that really they did not contain any high mass prestellar core, but however their total masses are lower than 200 solar masses. So it is questionable, in my opinion, whether they have the capacity to form high mass stars. But then we went to this big guy. So this seems very similar to the previous one, but it's actually almost 3 times farther away, and it contains more than 5,000 solar masses. So for sure, this is the potential of forming multiple, actually, high mass stars. So we targeted it with ALMA in band 7, and this is the zoom in the very center of the previous picture. And what you see here is the continuum emission in color scale. And you see that the continuum has some peaks, and almost everywhere where you have a peak, you have a star symbol, meaning that there is a protostar there. Ortho H2D+ emission instead is shown in contours, and you can see that not always there is a one-to-one comparison. And this is because sometimes the continuum peaks are actually not peaks in density, but are peaks in temperature. The protostar is there, is heating up the gas. You don't have Ortho H2D+ anymore, but in continuum you have a very bright spot. So we ran some dendrogram analysis using chimes to infer the position of the cores, which are shown here with these white contours. We found 22 of them. And based on the 0.8 millimeter continuum, we estimated their properties. in particular in terms of density, which you can see here. So all the cores are denser than 10 to the 6. This is because we selected them using a high density tracer. They are not so massive though. We have some 15, 30 solar masses object, but nothing more than that. And in particular, they are all very unstable. So the virial parameters estimated as the ratio of the thermal to gravitational content is well lower than 1, which means that these objects are not virialized at all, are likely already going towards the gravitational collapse. So these results are really not in agreement with a turbulent core accretion model, but they fit very well in a scenario of clump-fed. You have a number of low mass cores that evolve very rapidly, and whilst they are in protostellar stages, they will keep accreting masses. So we could do something more about this, which is we combined what we just saw with information coming from another very abundant ion, is N2H+, which this is a slightly lower density tracer, so what we are looking at are not really the core, but is the gas that is embedding, the clump scale gas in which the core are formed or evolve, okay? And what we did basically is that, first of all, we fitted this transition using a multi-Gaussian approach, because unfortunately, along the line of sight you have multiple velocity components, so you have to perform pixel per pixel component analysis to fit the spectra. And then these results of this fit were given as an input to a hierarchical clustering code. So a friend of friend kind of code, which basically you give it a number of points and it will group them based in closeness, in position, so RANDAC, in velocity, and in velocity dispersion. The goal of this code is to reconstruct the hierarchical structure of your source, okay? And I hope you find this as cool as I find it. So this is the result. So what you see here is a PPV plot. So you have right ascension on this axis, declination on this axis, so sky. And the third axis is the velocity, okay? And each small point is one Gaussian component. So it's one fit to one line, pixel per pixel, but in each pixel you have more than this. So they tend to overlap spatially, okay? The different colors are highlighting the different hierarchical structure, so the coherent structures in space and velocity that the core found. And you see that there are 5 of them, the big ones. There were smaller ones that I masked. And the black dots, finally, are the prestellar cores, and the magenta diamonds are the protostellar cores. So you see that what is going on inside something as big as and complex as this is a mess, so, essentially. So you have multiple coherent sheet and filament of gas, all active in star formation, and in particular, they're very active when they are intertwined. So when they collide, when they are interacting, they form a lot of cores. You could never see something like this using just continuum, right? So it's just having access to lines that give you such powerful technique to dissect something as complex as the structure of these eye master for mean regions. So, so far I spoke about how we can use molecules to trace physics, basically dynamics, kinematics, and so on. Of course, I am an astrochemist, so I'm very interested also into chemistry. And of course, molecules brings a lot of info concerning this. And in particular, I am very fond of fractionations processes, and I will just give you a little hint of what we're talking about. So the idea here is that with fractionation, with isotope ratios, I will explain in a minute what I mean, with isotope ratios in molecules, we can sort of follow this is the same picture we saw before, follow this process in the sense that we can try to establish a link of what we see, of the material that we see in present day's form stellar system and pre-stellar sources from where they were born, okay? This is the general scheme. And fractionation is simply the alteration of the isotopic content of a molecule, okay? If you have a molecular compound and you change one of these elements with an isotope of that element, a stable one, you form an isotopologue, okay? For instance, you can substitute hydrogen with deuterium, and instead of water, H2O, you have semi-heavy water, HDO. In nitrogen case, what we are talking about is substituting 49, which is by far the most abundant isotope, with a much rarer 59 element. And the point of nitrogen fractionation is that by observing it in the space and in the solar system, we realize that its isotopic ratio varies a lot based on environment and species targeted. And this suggests that you can really use to link back in time where the reservoir of gas were coming from at the moment of planet formation. So just look at this. So this is a plot of 49/59 ratio. The first few things I would like you to focus on is, first of all, this line at 440. This is the protosolar nebula. This was measured in the solar wind. So we know it's correct. And this is the N2 in the Earth atmosphere. Of course, N2 is a major component of our atmosphere. And already in the Earth atmosphere, we are down with respect to the protosolar value of a factor of almost 2. This means that some chemical processing must have happened during the formation of Earth and its surrounding atmosphere. Then if you go to space, we see values scattered everywhere. Here in blue are pre-stellar sources, and in red, protostellar ones. You can see that nitriles, HCN and HNC, are usually very enriched in 15N. This can be explained with chemical code, because HNC and HCN are not formed from N2 for molecular nitrogen, but for nitrogen, N. And so they have a different reservoir of gas from which they come from. But then you go to diazenylium. Diazenylium is N2H+, we saw it before, and you see this point here up to 1000. There is no chance that you explain it with any chemical code I'm aware of. And this, however, comes directly from N2, so this should be tracing the bulk of the N2 gas in prestellar sources. But of course, it was just one source, so maybe it's just an outlier. Maybe something went wrong when we observed it. So we went back to add a few more prestellar cores. Unfortunately, this is not fortunate or unfortunate, how it is. These molecules are, of course, extremely rare. So their emission is about tens of millikelvin. So you cannot do a survey of them. You take 5-8 hours per source to have one spectrum. But we measured these in 3 more cores, and you see that all the values are well above the elemental value. So what is happening? For some reason, in prestellar gas, N2H+ is very depleted of 15N. Well, a possibility is that in this situation, you destroy the 15N bearing species, N15NH+, much faster than N2H+. In this case, you would have, of course, an increase of the ratio. Let's see how we destroy these molecules. So these are the main destruction pathways. You have reaction with CO and reaction with free electrons. We call this dissociative electronic recombination. And when the gas is warmish and not so dense, the dominant reaction is the one with CO, because you have a lot of CO around, okay? But when you go at very high densities and low temperature, CO molecules love to stick onto the surface of dust grains, and they form ices, and they are completely gone. 99% of CO is gone from the gas phase in something like L1544. So then in those situations, this reaction that dominates. And if the reaction rate for these two would be different for some reason, of course, you could destroy this species faster than this. And in order to test this hypothesis, we went and we detected the same molecules in protostellar cores, because this is warmer and therefore you should have more CO around and the value should go down. And in this is what we observed. So these were the previous points that I showed you, and they have an average of about 770 or 50. And here are 6 protostars, low mass protostars. The values are significantly lower, and they're average is statistically lower than in prestellar sources, but and also incidentally consistent with the elemental value of 440. So we were very happy when we found this. Unfortunately, we still are missing a lot to understand nitrogen chemistry, and this is what we're currently also working on. Because then I went to the Green Bank telescope in West Virginia, and I observed ammonia. Ammonia is a different molecule because it's not an ion, it's a neutral species, it's way even more abundant than N2H+, but it's formed also from N2. So in principle, just looking at this, it should have a similar fractionation, let's say, a behavior. But this is always L1544 seen in its dust thermal distribution in white, and this is the ratio, the isotopic ratio of ammonia. And as you can see at the center, we are about 400, 500, which is not consistent with the 1000 of N2H+, but it's consistent with the elemental value. And also, you cannot really appreciate from here, but I did some higher signal-to-noise ratio study to show that indeed, when you go at lower densities, this ratio goes down, while instead it should go up. So we are still trying to work out to then answer these two key questions: why this molecule behaves so differently than the previous one, when it should not really, and second of all, what is causing this spatial variation? It might be UV field impinging on the core, for instance. So I'm now coming to an end. And I hope I show you through my talk how we can really use molecules to say a lot about how stars are formed, especially in the Milky Way, of course, but possibly in the future also elsewhere. And the number of properties that we can probe using them is tremendous, in my opinion. So you go from physics in terms of density and temperature, you go to all the kinematic studies, turbulence, gas flows, and so on. And finally, of course, they are carrying a lot of information about the chemical evolution. And so I'm finished here, and I'll be happy to take questions, if any.
Thank you very much, Elena. Very nice talk. Any questions or comments or feedback?
Thank you, very nice talk. It was just when you showed some spectra with the C18O and then the other line, which was optical thin, thick and thin. I didn't get why the C18O, because it's less abundant, is a better tracer of the Gaussian.
Oh, no, so...
did I miss it?
Yeah, no, sure. For me, I mean, I work on this. So let's say like this. So let's say that depending on what you want to trace, you want to choose different tracer, of course. Not only in terms of chemistry, but also in terms of dynamics. So optically thin lines, it means that everything, all the photons that are emitted comes to you. So they don't take any alteration in their spectral profile based, for instance, on the velocity at which the gas that they encounter moves, okay? So what they do is that they trace simply the velocity of the source, averaged within the beam, of course, because you have to think that we are in single dish, so the beam is pretty large. Optically, and C18O is optically thin because, of course, CO is very abundant, but if you divide it by 1000, it's not so abundant anymore. So this is an optically thin line, more or less, or barely optically thin.
So then CO would be optical thick.
CO is so optical.
Okay,
CO is like this.
Yeah, okay.
And some things, because CO it's everywhere, so you probe not only the source, but everything on the line of sight. So CO is...
Because CO is abundant, CO18 will still be abundant enough to probe still the main velocity then?
Yes, it's still definitely abundant enough, but you get rid of basically, so you have to imagine that you have a onion, and when you have, so with CO, everything below the very thin surface layer, you don't see it because it's completely absorbed. Okay, so the photons are just here doing like this and they don't exit. Only from here, a few photons exit. So if you want to go deeper, you have to go to something which is not CO. HCO plus, unless you want to study, for instance, kinematics, because what happens is that HCO plus, for instance, is not as abundant as CO. It's about 3 orders of magnitude less abundant, but still is fairly abundant. And what happens is that the photons that are emitted are absorbed at different velocity depending on where the velocity at which they were emitted and the velocity of the gas that they are encountering. And by this interaction, this produces this very peculiar line shape, which are basically how broad they are and how different the height is directly mathematically related to the infall velocity. And so this is how I do use it. Just a bit caveat, concerning the optical thickness of a line, the abundance of the molecules is not the only thing that determines it, okay? There is also the critical density that plays a big role. So it's a combination of how abundant the molecule is and how high or low its critical density is.
Okay, thanks.
Thank you.
How many different isotopes can you observe this way? So you've now said oxygen 16, oxygen 18, nitrogen 14, nitrogen 15. How many others are there potentially to be observed?
In principle, many, but telescopes don't like to give me hundreds of hours. So no, the main ones are 12C and 13C. They are the only stable ones that can be detected in space. For oxygen, there is 16O, 17O, and 80O. 17O, however, because of its spins, cause further troubles because the molecules bearing 17O are hyperfine, have an hyperfine structure, which can be interesting for some reasons. Then you have 40N, 50N for nitrogen, sulfur, 32S and 34S. Deuterium, of course. Deuterium is by far the most abundant and can be detected very well. And let me think. No, these are the main one. Yes.
Okay, thank you. Yeah, I work on nucleosynthesis
Mm-hmm.
in stars, so this
Okay.
is why I'm like, if you observe certain abundance ratios, it can be a feedback.
Yeah.
So
Actually,
that's why I'm
I mean,
curious.
your work is fundamental because it sets the elemental value, right?
Yeah.
So, because and actually, I mean, I call the elemental value 400, but this is actually also in the solar system neighborhood. If you go in the galaxy, you have different, depending on the age of the stars there, you have so yeah, we have a lot in common.
Thank you.
Thank you.
Any more questions?
Thanks for a nice talk. I'm not an expert, but I wonder if you go to the slide where you show the fits with your velocity field.
You
So
mean
this
this?
double? No, the double peak. No, I
Yeah.
just
Here.
yeah, here. What's the dynamical information in this velocity field, and does that allow you to derive some differential velocity during the process, or what goes into the prediction in terms of?
So how this is derived?
Yeah.
Oh, this is basically this is a Bonner-Haber sphere model. So what they did is that this work from Eric Quito and Paolo Caselli. So what they did is they took a spherically symmetric Bonner-Haber sphere and they make it collapse, reaching different densities at the center, and then they extracted the profile and they fitted them against water, CO, and the continuum, of course, because of the density, and they chose the model that best fitted this, which is the one shown there, basically. So this is the profile that comes from having a Bonner-Haber sphere.
But so, I mean, I guess my question is, if you were to change the way that the dynamics works, I guess you have some degeneracy in the way you set it up.
Yes and no. There is some degeneracy in yes. They modeled, so for instance, later work, they use a Bonner-Haber sphere, an isothermal collapse model, What was this? A third model, and not all of them fit at the same time. So there is some degeneracy, yes, but you can disentangle some of it, especially when you use many lines. Because if you use many lines, each of them will probe a different depth in the source, and therefore it will constrain a little bit of this. And so, of course, this is a bit ideal, but in general, multi-line tracing will allow you to, of course, constrain this much better along the line of sight.
Any more?
Hey, thanks again for the nice talk. I was curious about the massive star formation results that you have. So in the sense that there are these two moles, and you favor the, what was it, the core accretion one instead of the turbulent accretion?
Yes.
So I'm curious more or less in the long-term evolution of the systems. Do we expect some properties, like in terms of multiplicity of stars after the star formation process?
Okay. I'm not an expert on what happens when the gas is not there anymore. Of course, so what I'm interested in is, more the pre-stellar phases. So I'm honestly not familiar with what the models predict in terms of for instance, multiplicity of system. My guess is that something like the turbulent core accretion, where you have one massive core that collapses as a whole, it should not fragmentate, in theory, otherwise you will never form massive stars. Whilst there, you have something much closer to low mass star formation in a sense, is simply that the environment around is so dense enough that you are accreting at a very fast pace. It is my guess that they would make distinct prediction of how the final stars would be, like in terms of clustering, but I cannot give you now an answer.
Okay, thanks.
Any more? I have a question myself, actually. Can you show your beautiful 3D plot again?
I like it a lot.
So if you would not have drawn the colors, I'm not sure I would be able to do myself, in the sense that how do you decide when one component stops and the other starts? Is there a hard rule, or is it?
So the way the code works is that it takes 2 points and it asks itself how distant they are in 4 dimensions, where only the 3 of them are shown here. So what you see here is PPV, so position, velocity, but actually the code cluster also in velocity dispersion. So what can happen is that this, for instance, this I know because I remember by heart, this component and this component here has very different velocity dispersion. This is very quiescent, while here velocity dispersion are larger. So the code distinguishes them as belonging to different entities and clusters them.
Okay, good. Yeah, thanks. Any more questions or comments? If not, then let's thank Elena again. Thank you very much.
Thank you.
So she will still be here for a few hours, I think, or 1 hour or something like that. So if you want to talk to her, please, you can find her in my office. Very nice talk, thank you.
Thank you. I liked it a lot as well.
Simply put, yeah, exactly.